In this video, we're going to do a quick extension of something that we've looked at before. So before, we've taken a look at how we can convert moles to representative particles, in other words, for example, atoms, by multiplying by Avogadro's number. And if we're given the number of particles, we can divide by Avogadro's number to get the number of moles that is. We've also taken a look at if we start with moles, we can multiply by the molar mass, which we get from our data booklet, this number. And if we're given the mass to start, we can divide by the molar mass to get the number of moles. Today, we're going to sort of make it two steps. We're going to start with particles and ask ourselves how much mass do those particles have, or if we start with mass, how many particles are in that mass. So we're just going to be combining the equations or sort of the calculations we've done before. So here we have an example of how many atoms are in a gold bar with a mass of 1,000 grams. If you remember back earlier in class, we took a look at how gold is produced, and it's a very environmentally destructive process. So you get that one sort of 1,000 grams of gold by destroying, a lot of land. How many atoms are actually inside that gold bar? So what we want to do is sort of imagine this as sort of a map, this mole map here. So what we have here is our beautiful little electric car, which hopefully will start moving for me. No. Let's try again. Oh, good. Okay, you're gonna move. Okay, good. Okay, so in this question, you can sort of think of it as they've given us the mass, so we're starting with mass. And they want to know how many atoms, which are like our representative particles. So the way this map works is you start here and you need to get over there. So you have to follow the map. So first we're going to have to take the mass and divide it by the molar mass to get moles. And then we're going to have to multiply by Avogadro's number to get the representative particles. And that's how we're going to do this. So we start off with our 1,000 grams. We're going to divide by the molar mass, like we just said here. The molar mass, again, we take from over here. Gold has a molar mass of 196.97 grams per mole. And then we're going to multiply it by Avogadro's number. And when we do that and we type it in our calculator, 1,000 divided by 196.97 and then times by 6.022 times, or to the exponent 23, we get that answer. So we get 3.057 times 10 to the 24 atoms. So if you think about it, that's how many atoms there are in a 1,000 gram or 1 kilogram bar of gold. Now, if we were to instead switch over to silver, again, still has to be mined, but I'm not sure if it's as destructive as gold mining. How much would a silver coin weigh? So now we're just looking at a coin if it had this many atoms in it. So 7.12 times 10 to the 24. Well, this time, if we think about our map, we're starting with the number of atoms. So our cars, or sort of our map, is starting here. And then if we want to, oh, everything got moved there, sorry. And if we want to find the mass, we're going to have to divide by Avogadro's number, and then we're going to have to multiply by the molar mass to get the mass. So let's type that out. So we started off with the atoms, we multiply by 1.07 grams per mole, and we divide by 6.022 times 10 to the 23. So that was sort of our first step. We're trying to combine this all into one equation. So we divided by 6.022 and then we multiplied by the molar mass. And that together will equal 12.75 grams. Now again, you want to make sure your significant figures are always correct. So for example, here we were multiplying and dividing, so we have to use the least number. So here had 3, here had 4, here had 4, so we're going to have to use 3. So we're going to have to round this one to 12.8. Let me just check here, 12.753, yeah. So that will round to 12.8, just double checking that. And checking our significant figures here, again, divide and multiply, so least numbers. So I have 1, 2, 3, 4, 5, 6, 7 significant figures here. All of those zeros are significant, and then 5 here and 4 here, so 4. And my answer has to be in 4, 1, 2, 3, 4. So it's already like that. The other thing that I really suggest you get in the habit of is canceling out your units, checking that they actually cancel out. So for example here, grams divided by grams, and moles are canceling out with moles here, so you end up with exactly what you're looking for. Basically, the students that usually achieve highly, the highest bands, they always check their units for cancellation, because by doing this, which we also call dimensional analysis, you realize if, for example, you had to convert something and you didn't realize it at first. So for example, in this question, if instead of writing it in grams, we had said how many atoms are in a gold bar with 1.000 kilograms, with a mass of 1.000 kilograms or something like that. What you would have, if you had just written down kilograms up here, you would have realized by dimensional analysis that kilograms will not cancel out with grams, so you'd realize you'd have to do another sort of conversion step. So these are sometimes little extensions of questions that try to differentiate between a higher level student and someone who just has a basic understanding. So I suggest getting into this habit so that you know if your units cancel out, you end up with the answer you expect. So we expected representative particles, that's what we ended up with. And the same thing here, so atoms divided by atoms, moles, we end up with grams, and that's what we expected because mass was in grams. So everything works out that way.